Welcome. The topic for today is matrix differentiation. The basic idea of matrix differentiation is that we want to have rules that allow us to manipulate expressions defined in vector or matrix terms in the same way that in single variable calculus you learn rules to differentiate single variable functions, and those allow you to solve optimization problems, for example, by differentiating and solving for the derivative being equal to 0. So we're going to start out by talking about what the derivative of a multivariable function is. So suppose you have a function from Rn to Rm. So it takes in multiple inputs and it gives multiple real values as output. The derivative is going to be the matrix you get by taking all the partial derivatives you can and arranging them into a matrix. For example, if we consider a function like f of x comma y equals 2x minus y comma x cubed comma x sine y, then the derivative matrix for this function is going to be the derivative of the first component. Both ways we can do it, with respect to x and then with respect to y. Then the derivative of the second component with respect to x and with respect to y. And the derivative of the third component with respect to x and with respect to y. So the main thing you would like out of a derivative is some property like this. If you have f of x plus h minus f of x, so we're measuring how much the function's output changed when we change the input by a small amount, h, you'd like for that to be approximately the derivative times the vector indicating how much we changed by. So that's the first thing we're going to investigate numerically. And we'll find that indeed this identity holds. So we're considering this simple function. F of a vector x is equal to the first component of x squared plus the second component of x squared. So in more traditional calculus notation, this would look like f of x comma y equals x squared plus y squared, or maybe f of x equals the first component squared plus the second component squared. And what we're evaluating here is how much the function changes when you go from a base point of 3.1 comma half to 3.101 comma 0.51. So there's a small change in input and we want to measure the resulting change in the function. And of course we can just directly compute it, but what we'd like to investigate is whether in fact the derivative can be multiplied by the displacement vector to get approximately the same result. So the derivative of f with respect to x, the first component is going to be, maybe it's easiest to think about in this representation. The first component is going to be 2x, because if you differentiate x squared plus y squared with respect to x, you get 2x. Similarly for the second component, 2 times the second component of the input. So coming back over here, the first component is just going to be 2x1, and the second component is going to be 2x2. And notice that we have this prime here. That is transposing this vector. So instead of a column vector, we want a row vector, and that's coming from the definition. Notice in the definition, across a row, the component is the same. So you pick a component, you differentiate with respect to each variable, and you put that into a row. If you have multiple components, you get multiple rows. In this case, we just have one real number coming out. So this is m is equal to 1. And so we should have a single row with 2 components. And if we evaluate this function, just to see what's going on here, at some vector like 3.1 comma 0.5, what it's going to return is called an adjoint. So that's a vector that has sort of been transposed and is poised to multiply a vector on the right. We're going to evaluate that derivative at the base point, which is 3.1 comma 0.5. And we need to multiply that by the displacement vector, which is 0.001 comma 0.01. And we're just reading off the difference between this vector and this vector. And sure enough, we get a number that is quite close to the actual result. So it's slightly off because the step size that we took is positive, and this result is just infinitesimal. But if the displacement vector were even smaller, the error would have been even smaller. Notice here that we get to do this, because of the way we set it up, we get to do it exactly like in single variable calculus, where you just multiply the derivative by the displacement and you get the first order change in the function's value. There's no need to use a c dot here like you would have done in a multivariable calculus class. Instead, you just define the gradient to be transposed, and then that allows you to use regular multiplication. So we need to build up a suite of tools for dealing with matrix differentiation. And the first one we're going to look at is just what happens when you differentiate a linear function. So this comes up pretty often. And the result is what you would expect. When you differentiate ax, you get a. And to show this, we just take a look at a general example. So if we take the derivative with respect to x of ax, that means we're taking the derivative with respect to x of, let's give ourselves names. And to come up with the result here, we need to take the derivative of the first component with respect to each of the variables. So when you take the derivative with respect to x1, you're going to get a11. With respect to x2, you're going to get a12, and so on. And then when we move to the second component, we're going to get the same thing. It's going to be the second row. And finally, we get the last row. So we just recover the matrix A back. So that checks out. In problem 3, we're asked to show that the Hessian of a function can be written as the derivative with respect to x, and then transpose and derivative with respect to x of the function. So let's take a look at that. If we take the derivative with respect to x, and then transpose and take the derivative with respect to x, so the first thing we get is a row vector whose entries are the derivatives with respect to each component. And then we need to transpose that to make it a column vector. So with all of these formulas, the essential assumption is that your function that you're taking derivative of is going to be arranged in column layout. If we take this derivative, we get the derivative of the first component with respect to each variable. So that's going to be with respect to x1 and then x2. And that is indeed the Hessian matrix. So the Hessian is defined to be the matrix of second order partial derivatives of f, and that's exactly what we have here. So in problem 4, we're given another rule. So we have the product rule here. And the product rule is quite similar to the product rule for single variable calculus, but you have to be careful to put things in the right place. So it's, if you take the derivative of u transpose v, where u is a vector valued function of x, and so is v, then you get u transpose times the derivative of v plus v transpose times the derivative of u. And it has to be in that order. In single variable calculus, you're dealing with real numbers and everything commutes, so you can write this in lots of different ways. In matrix calculus, you can't. It needs to be like that. And the only thing you could switch around is this whole second term and this whole first term, of course, since addition is commutative. So we're given this rule. We're not going to show it here. It's a little bit tedious to write everything out, but it's just a matter of expanding the coordinates here and applying the old-fashioned product rule and sort of packaging everything back up. This is called a quadratic form, and the reason we're going to be interested in this sort of expression is that it comes up in Taylor's theorem. So if A is the Hessian and x represents the displacement vector that says how you've moved away from your base point in Taylor's theorem, then this is the quadratic term. So last time we talked about how you want to eigendecompose that middle matrix in order to get some insight into how this quadratic function behaves. And in this case, we're going to calculate the derivative. And in the next problem, we'll make use of that idea. So with the product rule and the other rule that we just discovered, we can work this out. So if q of x is x transpose times ax, then the derivative of q with respect to x is going to be, let's apply the product rule with this part as u transpose, and this part is v. So we're going to get u transpose times the derivative of v plus v transpose times the derivative of u. And the derivative of ax we just discovered is a, and so ax transpose is x transpose a transpose. And then the derivative of x with respect to x, the easiest way, in my opinion, to do this is to slip an identity matrix in there so that it fits the form of derivative of matrix times x with respect to x. And we know that that derivative is equal to the matrix. So this tells us that, sorry, I forgot the transpose there. This tells us that the result is x transpose times a plus a transpose. And assuming a is symmetric, this is going to be equal to 2x transpose a, since a is equal to a transpose in that case. So let's connect this up with Taylor's theorems. So the basic idea of Taylor's theorem in single variable calculus is that if you want to approximate a function with a quadratic polynomial, you should choose the quadratic polynomial whose derivatives match the function. So you can match the 0th derivative by making the constant term correct. You can match the first derivative by making the linear term correct. And you can match the second derivative by making the quadratic term correct. And for functions of multiple variables, we can apply the same idea. We start at the correct place, and then to first order, we move in the correct way. And notice this formula at this point is totally analogous. We have the displacement vector x, and then we have the derivative evaluated at the base point, which in this case is the origin. And they're just being multiplied. The second order term requires us to reorder things a bit, though. We saw this last time. So we get the same 1/2, and x squared here turns into x transpose on one side and x on the other side. And the second derivative becomes the Hessian here, h, which is evaluated at the origin. It's dropped the of 0 notation there. So the point here is that we want to show that if we differentiate this expression twice, we get the same derivatives as if we differentiated the function f twice. So again, we want to take the Hessian of this whole expression. So we want to differentiate it with respect to x, and then transpose the result and differentiate it with respect to x again. And we want to, hopefully we'll come out with h as our answer, because the Hessian of f at the origin is h, and we want the derivative of this thing to match up with that. So the constant term and the linear term are going to go to 0 when we take the second derivative. I will leave that part out of it and focus on this last term, but you could also just apply rules there and get to the same result. So first, taking the derivative with respect to x, we get 1/2 times 2x transpose h, all transpose, and then we need to take one more derivative. And that step just comes from the previous exercise. Taking the transpose, we just get hx, because 1/2 and 2 cancels. And that derivative is just going to be h. So that checks out. And you can also show that the first derivative of this quadratic polynomial matches up with the first derivative of f, and of course the 0th derivative matches up as well. So this is the right formula for a quadratic polynomial that matches all the first and second order derivatives of the function f at the origin. In this problem, we'll start to get into applying matrix calculus in a situation that has some real-world applicability. So the idea is that we're looking at this objective function, the norm of ax minus b all squared plus lambda times the norm of x squared. So the idea is that A has some columns. It's a matrix with some columns, and x is telling us how we're combining those columns in a linear way to try to reach b. And ideally, we could just make ax equal to b if b is in the span of the columns of a, and then that first term would be 0. So if lambda is 0, so the second term is not there, and b is in the span of the columns of a, then this is just solving a linear system. So here we're sort of generalizing the idea of solving a linear system. If b is not in the span of the columns of a and lambda is still 0, then we're just trying to get ax as close as possible to b. So that value of ax in that case is going to be the projection of b onto the span of the columns of a. But when we put the lambda magnitude of x squared in there, it changes things because that influences x to try to get small. So its coefficients need to be smaller. If it wants to have really big coefficients to make ax be close to b, this term is telling it, don't do that. Be more realistic, have some smaller values, and still do your best. So if lambda is 0, then we're just getting ax as close to b as possible. And as lambda increases from 0, we start to decrease our coefficients. And eventually, if lambda is really, really huge, then we have to use tiny coefficients for x, because this term will be enormous otherwise. And this term starts getting really ignored, and we're just going to get very small coefficients in the vector x. So let's work this out symbolically and see what happens. So the first thing we're going to do is rewrite these norm squareds as a vector transpose times itself. So this is going to be ax plus b transpose. Sorry, this should be a minus. Ax minus b transpose times ax minus b. And this is going to be x transpose times x. Now we can apply the product rule. It's going to say the first vector transpose times the derivative of the second one. And then we're going to get another term, but that term's actually going to be the same because these two vectors are the same as each other. So we just put a 2 here. And similarly for the second term, we're going to get 2 lambda x transpose times the derivative with respect to x of x. And so that's 2ax minus b transpose. And then the derivative of ax minus b is just going to be a. And we didn't show that, but I'll leave it as an exercise. If you differentiate a constant, you get 0. And then this second term becomes 2 lambda x transpose. So we can simplify this a bit and say that when we distribute the transpose and multiply this out, we get So we can take this expression, which represents the derivative of the function we're trying to minimize, and set it equal to 0. So in this step we transposed both sides, and in this step we applied the inverse of A transpose A plus lambda I to both sides. The problem statement tells us to not worry about invertibility there. So we get this formula, and we can investigate what it looks like in the context of a specific example. So this is problem 7. So for the matrix A and the vector B that are given in this example, so 1.1, 1, 1, 1, and 0, 1, we're asked to figure out what happens when we solve the equation ax equals b. And the linear solve operator in Julia is the backslash. And what we find is that we're being asked to use negative 10 of one of the columns and 11 of the other column in order to reach this vector 0, 1. So we can plot this. We'll just use the function defined below to see what's going on. So we have these two columns of A, which are very close to each other, these orange and blue vectors here. And we're trying to form a linear combination of them that reaches this green vector. And of course, you can do that because they're not the same vector. They are not parallel. They span R2. And that means that any vector, including this green one, can be realized as a linear combination of these two. However, we have to do it in a way that in some situations would be undesirable by adding quite a lot of one column and a negative amount of the other column to sort of cancel out what's happening in this direction that both of them represent quite accurately in order to leverage what's going on in the difference between them to reach in this direction. So you can see that even more pronounced if you make them even closer to being parallel. What's going to happen is that you're asked to use negative 1,000 of one of them and 1,001 of the other one. And in data science situations, this sort of business is just not ever going to be helpful. The idea is that the columns of A represent features for some number of observations, and you're trying to combine those features to match some response variable B. And if the model is telling you that you should use negative 1,000 of one column and 1,001 of the other column, that means that it's leveraging the difference between those two columns in order to try to match the response variable. And that's never going to be meaningful because your precision on your numbers is not that high. And you want a way to sort of squeeze that out somehow and say, don't use all the directions of A. Just use the directions that are meaningfully represented in A. And this is a particular approach to doing that. So let's see what happens visually. So we set up our matrix A again, 1.1, 1, 1, 1, and B 0, 1. So we're trying to, again, form a linear combination of the columns of A to match up with B. And what we're going to do is solve this equation. So we have this formula here, A transpose A plus lambda I, and then in numerical computing you want to avoid doing the inverse almost all the time. Matrix inverses are expensive to compute. In this case it doesn't matter that much because it's a small matrix and it can handle it, but just for good hygiene we'll use this linear solve operator instead. And we're looking at the vector B that we get for that particular minimizer. So X gives us the weights to minimize the expression, including the penalty lambda times the norm of X squared. And B is telling us the vector we actually reach when we use that particular minimizer. And what you can see is that you get some pretty desirable behavior. So in the extreme where lambda is really small, so K is the log base 2 of lambda here. So if K is really small, so lambda is really close to 0, you basically get the vector 0, 1. So you're able to reach it because you're not penalizing the weights at all. And this is with X having some two oppositely signed very large components. But as you increase lambda, the optimization starts to move away from 0, 1, and the reason for that is this shorter vector is going to be coming from an X value that has much smaller coefficients. And at some point you have really sort of almost exactly what you want. You'd like to say that this purple vector is the vector that best matches the green one while still being in the directions that are meaningfully represented by these this orange and blue vector. So the orange and blue vector are clearly reaching out in the sort of northeast-southwest direction. They're not really capturing that other direction except by virtue of this really small difference between them. And if you stay in the northeast-southwest direction, this purple vector is as close as you can get to the green one. But then if you make lambda too large, what starts to happen is that the penalty term dominates and it starts to forget about trying to get close to the green one, and it just shrinks down. So the vector x is shrinking down to 0, and as a result, a times x is also shrinking down to 0.